Welcome to DEFUNCT. The machine rotating on your screen is the M4 Sherman tank. It was engineered to mass-produce victory for the Allied forces during the Second World War. But a single millimeter of misplaced steel turned this 30-ton mechanical marvel into a rolling death trap. Thousands of Allied tank crewmen became casualties. When struck by enemy armor-piercing rounds, early Shermans suffered a catastrophic burn rate of 60 to 80%. We are going to strip away the olive drab paint and the welded steel hull to expose a ticking time bomb hard-coded directly into the original blueprints. Initiate a longitudinal cross-section cut from the front glacis to the rear engine deck. Look at the internal spatial distribution. The American industrial complex prioritized rapid assembly lines, demanding a standardized chassis that could accept various power plants. They opted to install the massive Wright R-975 Whirlwind, a 9-cylinder radial engine, at the extreme rear of the hull. To transfer that 400 horsepower to the front-mounted transmission and drive sprockets, engineers had to run a heavy, rotating propeller shaft directly through the center line of the crew compartment floor. This single mechanical routing decision completely consumed the lowest, most heavily protected storage volume inside the vehicle. The designers had no choice but to displace the ammunition storage racks outward and upward. Isolate the sponsons. These are the overhanging structural shelves of the hull located directly above the track suspension system. The engineers packed 97 rounds of 75mm ammunition into these unarmored dry stowage racks. The shells were positioned right at the waistline of the vehicle, perfectly exposed on the flanks. Zoom in on the side hull armor protecting these sponson racks. Measure the thickness of the rolled homogeneous armor plate. It is precisely 38.1 millimeters thick. That is merely 1.5 inches of vertical steel, standing between high explosive ordnance and the outside world. Contrast this with the frontal glacis plate, which is 50.8 millimeters thick, and angled at 56 degrees to maximize effective line of sight thickness and induce projectile deflection. The side hull possesses 0 degrees of sloping to deflect incoming kinetic energy. Place this geometry into a real-world ballistic combat scenario in the bocage of Normandy. The Sherman side hull sits at the exact optimal impact height for every German high-velocity anti-tank weapon, from the handheld Panzerfaust to the towed PAK-40. The sponsons act as a perfect, unmissable bullseye, presenting a flat, perpendicular surface to enemy gunners. Now, extract a single M48 high-explosive 75mm shell from the sponson rack. We will render the thin brass casing completely transparent. Look at the lethal chemical payload packed inside. While the warhead contains a highly volatile explosive filler, the true danger lies in the tightly packed nitrocellulose propellant charge sitting at the base of the shell. Analyze the thermodynamic properties of this specific chemical compound. Smokeless powder possesses an incredibly low flash point compared to standard military high explosives, exhibiting extreme sensitivity to friction, shock waves, and rapid temperature spikes. The ignition threshold is mechanically unforgiving. A sudden influx of kinetic heat or a high-velocity spalling impact will instantly vaporize the brass casing and trigger an unstoppable molecular chain reaction within the propellant bed. Expand the three-dimensional camera view back to the full sponson rack assembly. You are looking at a tightly packed honeycomb cluster of highly sensitive chemical energy pressed directly against a flat, exceptionally thin wall of carbon steel. The dry stowage system utilizes bare metal brackets, offering zero thermal insulation or ballistic compartmentalization. There are no blast doors separating the ammunition from the crew. There are no blowout panels designed to vent explosive overpressure outward. The commander, gunner, loader, driver, and bow machine gunner are essentially sitting inside a sealed metallic pressure cooker, entirely surrounded by their own exposed ammunition. A single armor-piercing tracer round or a molten copper jet penetrating this 38mm steel box will bypass all crew survivability parameters. One single spark entering this specific geometric coordinate, and the laws of physics will instantly seize total control of the environment. Track an incoming Panzergranate 39, an armor-piercing, ballistic-capped projectile fired from the 88mm KWK-36 gun of a German Tiger I. Calculate the trajectory and the raw physics of the impending collision. The 10.2 kilogram hardened steel penetrator is traveling at a muzzle velocity of 773 meters per second. It carries over 3 million joules of kinetic energy. Impact is achieved at exactly 90 degrees against the Sherman's unsloped 38mm sponson armor. The physical laws of metallurgy dictate immediate structural failure. The yield strength of the rolled homogeneous armor is vastly eclipsed by the focused kinetic pressure of the incoming round. The German steel cap bites into the American hull. The armor plate buckles, then fractures, undergoing catastrophic plastic deformation. As the penetrator punches through the steel plate, it initiates a deadly mechanical phenomenon known as spalling. The kinetic shockwave shatters the interior face of the armor wall, creating a conical shotgun blast of jagged, razor-sharp steel fragments traveling at supersonic speeds into the crew compartment. But the spalling is merely the precursor. The immense friction of the 88mm shell forcing its way through the armor matrix generates an extreme localized temperature spike exceeding 1,000 degrees Celsius. A highly pressurized stream of liquefied metal and shattered tungsten blasts directly into the dry stowage ammunition rack. This molten jet makes direct contact with the brass casing of the first 75mm shell. The 1.5mm thick brass instantly disintegrates under the thermal shock. The nitrocellulose propellant inside is suddenly subjected to flash heating far beyond its ignition threshold. The chemical bonds violently sever. Solid matter transitions into expanding superheated gas. This localized rapid deflagration occurs in precisely 1.2 milliseconds. Switch the simulation to thermodynamic mapping. Watch the thermal energy radiate outward in an unstoppable exponential curve. The initial blast wave cannot escape the heavily confined geometry of the steel hull. The pressure violently crushes the adjacent 75mm shells inside the rack. The immense mechanical friction and radiant heat trigger a sympathetic ignition. Round number 1 ignites round number 2, which ignites 4, which ignites 16. Within a fraction of a second, all 97 rounds of ammunition stacked in the sponson suffer simultaneous catastrophic failure. We are calculating the instantaneous combustion of dozens of kilograms of high-grade military propellant and explosives, confined within a sealed 15 cubic meter metallic volume. Analyze the extreme structural consequences of this pressurized event. The sudden generation of thousands of liters of superheated gas creates internal pressures exceeding 10,000 pounds per square inch. The welded seams of the lower hull hold their integrity, forcing the explosive energy to seek the path of least mechanical resistance. The weakest structural link is the 72-inch turret ring. The massive shear force completely severs the retaining bolts. The resulting pneumatic blowout physically lifts the 15-ton cast steel turret completely off the chassis, throwing it vertically into the air. For the 5 men trapped inside the hull, the environment transitions from ambient temperature to a 2,000-degree atmospheric inferno in under 2 seconds. The sheer kinetic overpressure liquefies biological tissue and violently collapses human lungs long before the flames can consume the oxygen. This precise mechanical sequence earned the Sherman the grim moniker of the Tommy Cooker. German gunners joked that it lit up every single time. By 1944, the United States Ordnance Department had extensively analyzed these burnt-out wrecks. They realized that adding thicker armor plates would drastically overload the radial engine and shatter the suspension bogies. The engineering solution was not to stop the incoming kinetic energy, but to mathematically mitigate the thermal chain reaction. We are going to strip away the dry stowage racks and install the ultimate mechanical adaptation. This is the wet stowage system. The engineers relocated the ammunition racks from the exposed upper sponsons down to the floor of the tank, placing them beneath the turret basket where they were shielded by the road wheels and surrounding terrain. More importantly, they completely encased the new ammunition bins in double-walled steel water jackets. These jackets were pumped full of 35 gallons of a highly specific fluid mixture containing water and ethylene glycol antifreeze infused with a rust inhibitor. Analyze the fluid dynamics of an armor-piercing strike against this new geometry. When a molten metal jet penetrates the wet stowage bin, the hydrostatic shock instantly shatters the internal water jackets. Tens of gallons of liquid flood the storage compartment in milliseconds. The high specific heat capacity of the water aggressively absorbs the thermal energy of the molten shrapnel, rapidly quenching the flashpoint of the volatile propellant. It suffocates the spark before the exponential detonation curve can begin. This single brilliant manipulation of fluid dynamics plummeted the Sherman's catastrophic fire rate from a horrifying 80% down to a highly survivable 15%. The M4 Sherman was fundamentally flawed on the assembly line, but American industrial pragmatism ultimately adapted its mechanical anatomy to survive the slaughter.